Okay.
Are you going over everything or just like certain parts?
So I'm gonna write down kind of the units that we went over.
Oh.
And then I'll let you guys decide like which ones you wanna take a look at. Then I'll go from there. Come pull up a chair.
I like this format much better.
You do?
Yes.
Okay. That makes. I don't know. I'm not a fan, but like if you like it, that's awesome. We should do this more often then.
Was it us who did it, or was it a different class?
I think it's the people before us.
Maybe they were playing with our friends.
Probably. We're gonna get started then. So these are kind of the topics that we covered in unit 2. So from the first midterm to the second midterm, and that's what we'll be covering today. So if I don't know, what do you guys think? Was there anything that you struggle on or any questions from the exam that you still have? Any of these topics that you have no idea what that means when looking at it?
Two things.
Yeah, what's up?
This when how do I describe it? The conditional Bayes law and continuous distributions.
Mhm.
That's one, and then the other one being just estimators as a whole, and like the kind of like, I guess, a true or false practice or a review of those ideas.
Yeah, so we'll go over conditional distributions, the parameters and estimators, and then if we can go over the true or false from the last test. If that's good with you guys.
Awesome.
Anything else? Any other questions? I'm probably it's probably good to go over just continuous distributions in general. Because they're kind of like the really meat and potatoes part of this section of the course. So we'll probably go over that. But start there. Okay. Okay, so the basic equation of conditional probability when you are using a continuous distribution is so
And it was like so fun and I felt so special.
let me make sure I don't get this wrong.
Yeah.
Thanks.
Yeah. Otho, do you remember Bayes' law?
It's a the probability of A and B over the probability of the latter term in the given term.
Yeah.
A given B is a joint between A and B over B.
Okay. So these are essentially the exact same. Because with our joint probability or function, we find the probability of A and B together. We plug in X and we plug in Y, and we find that joint probability. And then with our marginal probability distribution function, that's just the probability of for example, yeah, if B is X, then it's the probability of X at any given point.
Do we take an integral at all, or?
So yeah, you'll need to get an integral to get this especially, because we are, normally we're given our like. Our PDF as like,
Here, why don't you do this, Spencer? Why don't you just do f of x, y equals x plus y? And then.
yeah, I have an example already written down here. So. So like, for example, if our equation is like. Squared, then to find the marginal probability of X, we would need to take the integral with respect to Y. Is that, you guys remember that,
Yeah.
going over that? Okay, so we take the integral with respect to Y, and then it's I guess we're gonna do over,
What's the bounds?
yeah, we're gonna do from 0 to 1. So we're just gonna do that, X, Y squared.
Should just be 2/3 x. I think,
Or
or is it the other way around? Yeah, the other way around, my bad. So, I was derivating.
One-third X, marginal distribution function. And so then to find a conditional probability, we would take X, Y, cube, or that one cube that's squared. And divide that by. Which just ends up getting us 3y squared.
Yeah.
That cool, that makes sense?
Or can you go over that again?
Yeah, no, yeah. So, to find this, we're usually given like this equation right here, which is our PDF. Our probability distribution function. And so to find the marginal probability of X, you take the derivative of your PDF with, or not derivative, take the integral with respect to Y. Over the bounds of Y, and then to get the conditional, you take your original and divide it by your marginal. And so then that just ends up to that. That makes sense. Cool, we good there on, yeah, what's up, Taylor?
I was just saying, good.
Oh, okay, sweet.
Fantastic. Oh,
So I just.
yeah, what's up, Spencer?
Just make sure, so the fx of x is where you take the integral with respect to y. Because it ends up
Yes.
with just x at the end.
Exactly. It's the same idea as, you remember when we had like our discrete distribution functions, and we'd add up all of the different probabilities of like x equals 0 for each like different value of y. It's the same idea,
Okay.
but like with an integral, because you're adding up an infinite number.
What, so like if fxy is the PDF, what do you call fx of x?
So this is the marginal distribution
Marginal
of x.
distribution.
Yeah, marginal distribution of x. So then if it's y, it's marginal distribution of y. And then this is like the marginal distribution of y given x.
Okay.
So,
we also might wanna do the test for independence.
right, independence, so
F of x times f of y
equals the original function, yeah, so like the rule for independence when you're working with the continuous case is your marginal distribution of x times your marginal distribution of y is equal to your probability distribution function. So if that's true, then you're independent for all intents and purposes. If it's not true, then you're not independent. And so there are some situations in which this is true if one of them is 0. And that, I think that came up on the midterm. That was one of the true or false questions. So,
The easiest way to do this is to just plug in 0 for x and y. And get the same answer.
yeah, so. Or, you could just, factor out the entire thing, which is always exciting.
Don't do that.
But yeah, easiest way is probably just plug it and see what's up. Okay. That's a brief rundown of continuous joint distributions.
Oh, do you wanna show the X hat or the X tilde one to get the CDF?
Let me see, yeah.
You know how like if we wanna
Where
find
it's
it
like
down-
something and then like. Is it from X to something or something to X?
Yeah, you substitute X tilde,
Oh, right. Yeah, so
probably a good idea.
this is our PDF, right? So our probability distribution function, it'll have like, so the way I visualize it is like, it's a graph. And so like, for example, this is our normal distribution, right? It's bell-shaped curve. The CDF is the area underneath any 2 points on this graph. So for example, if we want to find the area underneath xy squared, we would have to take the integral from the lower bound to a certain point. And so, let's say we want to find the 50th percentile. We would take the integral of xy squared. Wait,
Set it equal to 0.5.
right. You take the double integral, I think. Yeah.
No, wait, W.
No, yeah, so from lower bound, so for example, in this case, we have 0 to x. And we set it equal to 0.5. So that would end up being. Actually, does someone want to try it?
Try what?
Try doing that, just on the board.
What type of question would that be?
So this is if you want to find the 50th percentile. So I don't know what xy squared would look like. But for example, like this is our lower bound right here. That's so 100% of the data falls between these 2 points, right? So the probability of getting inside that is 1, right? And so you're trying to find the point where the probability, you're trying to find point x, where the probability is 50. So from here to here, you have a 50% chance of falling in there. And that's your 50th percentile. So like if you were trying to go up to here, that's your 90th percentile, right? 90% of the problem, like it's a 90% chance you fall between there and there. And that's how you do percentiles, continuous PDFs.
Why don't we use y instead of x for integrating it? Why, like, is this the 50th percentile just x? Or,
Oh, I guess you're right. Yeah, so this is a different variable. Sorry.
Is that X tilde?
In this case,
Possibly. I'm a bit turned around now.
Or no, doesn't that becomes X, but the normal X, the equation becomes X tilde?
in this instance, I don't think so because we have X and Y in the same equation. And so you have to do a little bit of funny things to make sure that works. If we were looking at, say, just the marginal distribution of X, then we would be able to. And we can make it a CDF and we can make it between 0 and the bounds of whatever X tilde. And we can plug in whatever we want for X tilde.
Okay, yeah, that's exactly right. So we're gonna do of the marginal distribution of x. So that's 3y.
I think it's just 1 over X or X over 3.
You're right, that's it. X, and then,
Put like a squiggly line on top of it too.
right, so because you're going to go up to the x, that's what we're trying to find, and then you're gonna kind of like,
And then put a D squiggly X.
right, that's right. And then so then to find that, you just integrate with respect to.
Which is pretty easy.
X to 0, and then you just end up getting 1/6 x.
Doesn't it go to X squared? Or
Right.
X tilde squared? It's kind of hard to say it.
And that ends up 1/6 x squared. So you can.
and then we equal it to 0.5 and then solve for x.
Yep. Okay, so that'd be. 5, so 3, square root of 3. So,
I think we had to put a K in front of it first when we first integrated it in order to have it scale properly.
Yeah, so the scalar K, that'll come at the beginning of problems like this sometimes, so it'll be like,
Will that be implied or will that be will it say solve for K or can?
Well, it'll usually have K in it.
yeah, so
So
you'll
solve
usually
for
like
K.
get this as your equation first. And then it will be like solve for K. And the way you do that is you take the integral, the double integral
Yeah.
with respect to X and then respect to Y. And
Within
then
the
set
bounds.
that equal to 1, and then you'll be able to find the K, which is just the scalar, which makes that possible. So. Are we good? Are we lost?
Slightly.
Slightly? It's fine.
Keep moving
Why, we can come back and do a practice problem on this, and I think that would be really good. But briefly, we're gonna go over parameters, estimators, that sort of stuff. Yeah, exciting, right?
You saw the test, right? Are we screwed?
I am not at liberty to say, but actually, I don't know if you're screwed or not. I don't know how well you guys are gonna do. I have full confidence in you guys, actually.
What's that confidence interval looking like?
I would say that of everyone in this room, my confidence interval is like 99%.
He has 99% confidence interval. That's good.
Yeah. I'm not gonna say 99% confidence interval of what, but it's 99%, that's for sure. That will take 6. Yeah, so, you guys actually have a little bit more of a framework now to understand the difference between like estimators and parameters. So, if we're thinking about it in terms of like hypothesis testing, right? What we're doing is we're trying to find the parameter. So for example, when we take a random sample of something and we're trying to find the true average, my favorite example is like true average height of BYU students, right? We could take a random sample of people at BYU and take that sample average, and that's gonna be a pretty good guess at what the true average is. Because that's a true number, we just don't know. There is like an actual medium height of BYU students, but like, we don't know what it is. The only way to find out is like,
Estimate and make an confidence integral.
exactly. So we do that by taking random samples, which are independently and identically distributed. You guys remember that? What's up, Spencer?
What is the definition of independently and identically distributed?
Yeah, so-
I work on that for the test.
Yeah, independently identically distributed means that you have this underlying distribution. So the distribution of people from which you're pulling your sample is independent of each other. So if you choose one person, it doesn't affect the chances of someone else being picked. So that's what independence means in this situation, is if you, like, for example, I choose Spencer out of my sample of BYU students, that does not affect Jerry's chance of being picked to be chosen for this sample. So like everyone in the sample, it's kind of like an independent thing, and then identically distributed, everyone in the sample is kind of in the same distribution. There's not like 2 different distributions going on in the sample. It's not like half the sample is normally distributed while the other half is like gamma distributed, right? Like that's not, it has to be the same underlying distribution. And then with that, if we have a big enough sample size, the central limit theorem, you guys remember that, says that like we can expect the sample mean to be normally distributed. And that's kind of the whole idea of hypothesis testing. Yeah.
Will we ever have to be like, oh, by the central limit theorem, we know that it must be normally distributed because it's such a big number?
I get the feeling we'll need it a lot for hypothesis testing. Yeah.
You probably won't need to say that in your hypothesis testing. I would like more focus on saying this is my null hypothesis, this is my alternate hypothesis. But if it mentions, if the test question like explicitly says like you're pulling from a like a uniform distribution, then and you still want to do your hypothesis test, you can say, well, even though it's a uniform distribution, by the central limit theorem, we can assume that the sample average is normally distributed. So then we hypothesis test. Cool. Trying to think what else. So then there are three aspects of an estimator: bias, consistency, and efficiency. And those are pretty straightforward. So the bias of an estimator is the expected value of that estimator. Minus the actual parameter. So in this case, we use like, if it has a hat on it, then it's gonna be your estimator, and if it doesn't, that's your population parameter. And so, this is the equation for bias. So let's say like we're using X bar as our estimator, right? So X bar is our sample average, which is we take 30 people, we add them up, divide by 30, right? And so the bias of X bar is equal to the expected value of X bar minus mu, which represents our population average. And the expected value of X bar is actually just mu, so then this is going to equal 0. And that's how you can tell if you have an unbiased estimator.
Sample mean is divided by n, is that right?
Yeah, so the equation for X bar is like 1 over n summation X I. Yeah. That literally just means you add everything up and divide by the number that you've added. So, the other aspect of estimators is efficiency. That's what it is. It's efficiency. And so, and that's a relative aspect. So you can't say something is, oh, this estimator is efficient. The efficiency is just the size of its variance. So if it has a really, really high variance, then it's less efficient than something else. But if it has a lower variance than something else, then it's more efficient, if that makes sense. It's a relative term, right on the board. Yeah, okay. So, variance of, say, theta hat greater than the variance of theta tilde. Theta hat is so in this case, theta tilde is just a different estimator that we could use. So, and then these two come together in the third aspect of an estimator, which is consistency. Spencer, did you have a question?
Isn't it whichever one is the smaller variance is more efficient?
Yes,
Because it's closer,
that's
like,
exactly
the
right.
variance is closer to 0, and so there's less.
Right, thank you, good catch. So yeah, if it's more efficient, its variance is smaller. So then the last one is consistency, so I'll just do. So consistency just means that bias and variance get smaller as your sample size gets bigger. And there are actually situations in which like you're gonna have an unbiased estimator, but it's cool because it's efficient. So you just keep getting a bigger and bigger sample and you'll get closer. But you don't need to worry about that for. Yeah, that's the definition of consistency, and that you could also consider it like as n approaches infinity, like bias approaches 0, just that sort of stuff. Any questions on that? Okay. Cool. Okay, do you guys want to go over the multiple, or not the multiple choice, like the true or false from the last test?
Sure.
Okay.
Yeah.
Real quick.
Yeah, what's up?
Consistency, does this apply like when n is equal, greater than or equal to 31, that we're, this applies to?
So when n is greater than or equal to 31, that's the central limit theorem. And that's a little bit different. So the central limit theorem is just that like. Actually, so the central limit theorem applies really mainly to X bar. And basically it says that as n is bigger than 30 for purposes of this class, then we can assume that X bar is distributed normally. So like, no matter what kind of distribution, so let's say like, it comes from a distribution that like looks like this. Like, like the population could come from a distribution that looks like that. But our average, so like, let's say we pull like, we pull a random sample from. 30 from like any point on this graph, our average. If we pull enough samples, is going to end up normally distributed.
You remember in class when we looked at the uniform distribution and we did it like 100 times, we just spammed it. Even though the distribution is like literally flat, like we went here, 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 here. And it just kind of stacked up in the middle. It looked like that. That's basically it.
There's like a ton of visualizations online. I can actually post a link if you guys want me to, of the way to kind of visualize the central limit theorem. But sorry, do you still have?
I have more question about consistency,
Absolutely.
because I'm questioning about what would it look like and as approaching it in that context.
Use X bar.
In X bar, like in terms of X bar or just in any context?
If it's like that, then it kind of makes sense.
Yeah, I guess as X approaches infinity or N approaches infinity there, then it just gets smaller and smaller and smaller.
Yeah.
Or sample variance is a good idea as well.
Um,
Over N minus one.
Right. I'm trying to think, I have a visualization of consistency. Yeah, so say like let's say that this is like our true mean that we're trying to find. And if we have an estimator that's like consistent, then this is like a low end. So like if this is a small sample size kind of distribution. But then as our sample size gets bigger, then it converges around that true point. So we're gonna get less variance and we're gonna get less bias around it. Or for example, there are estimators that are they start out biased, but they're consistent. And so it's like as we let's see if I'm drawing this right. Yeah, so as our sample size gets bigger, our bias becomes smaller. And we get closer to the actual value. Is that clear that up? Any more questions on this sort of stuff? Okay. Cool. All right, let's go over then the true or false. Okay, cool. I don't want to drop it because we want. So I'm just gonna paste this. So question one, X is a random variable, then correlation of X and 1/3 X equals 1/3. What is this? Yeah. What do you guys think?
It's there, the correlation is equal to 1 because I guess, whatever X is, it'll directly impact what the other side is, 1/3 X. And because they have such a direct relationship, it equals 1.
Awesome. That's a great intuitive way of thinking about it. Spencer, you had your hand raised.
I guess like my thought was like in class, we talked about correlation of x equaled 1. And so with 1/3, usually with correlation, you can just pull it out front. And so it'd be 1/3 times 1, maybe not.
Okay,
I don't know.
you're thinking great. So what you're thinking of is actually covariance.
Oh.
So the equation for correlation is covariance of XY over your standard deviation of X times your standard deviation of Y. That's
That's a row.
yeah, so rho is the Greek letter that we use here.
Oh yeah, did we go over how to do that? We need to go over how to get those for distributions.
How to get correlation? So it's gonna be the same idea with discrete and continuous.
Yeah.
So as long as you know how to do an expected value,
Oh, good.
then you should be good. And we'll go over that in just a second. But the idea behind this problem, like mathematically, is like covariance of X and then 1/3 X over X times variance the square root of. So these are our standard deviations, right? Because standard deviation squared is variance. So the square root of your variance is your standard deviation. And now the equation for covariance is the expected value of XY minus. So, yeah, the expected value. X times expected value of Y. So this is gonna end up equaling the expected value of 1/3 X squared minus the expected value of X times the expected value of 1/3, or not 1/3, just X. And the properties of expected values is you can pull that 1/3 out. And you could also pull that 1/3 out, so then it just ends up equaling 1/3 times the expected value of X squared minus expected value of X squared. So the 1/3 is, you can just pull this out on top. So that it's the covariance, 1/3 the covariance of X and X. Which covariance of anything with itself is just its variance. That makes sense, because it's the same equation for variance and covariance, you just put a different variable in. And then this variance, you can pull that out, but you have to square it. So this is gonna be equal to 1/9 variance of X, so the square root of that. And then the square root of 1/9 is just 1/3, so you can pull out that as well. And then these 1/3 cancel out. And it ends up just equaling the variance of X over the variance of X, which is 1.
You guys remember when we did stata and we did like we asked it to do correlation? And it gave us like the first value was like 1, and then the joint in between was like a value, and then the next one was a 1. Do you guys remember that?
Yeah,
That's exactly how I thought about this one.
Yeah.
You can't forget it. That's exactly how I got this one right. I was like, oh yeah, that's right. It's just,
The correlation of anything with itself is 1. So it's a perfect linear relationship. Okay, is that good? We good on number 1?
Can we explain how to calculate covariance one more time?
Yeah.
The shortened equation.
The shortened equation?
Yeah.
So this one right here?
Oh, I thought it was an equal sign in between that.
Oh, no. It's the
different.
expected value of X times Y minus the expected value of X times the expected value of Y.
Okay.
So briefly, like You guys remember how to do expected values with continuous functions?
You integrate it.
Exactly, yeah, you integrate it, but you also multiply by x.
Oh, yeah.
So like, for example, the expected value of like x is, if this is our marginal distribution of x, then to find the expected value of x, we take the integral of x times our marginal distribution in terms of x. And that's a lot of x's, but
I love that notation. Thank you so much. It makes me so happy. Your notation.
that's how you do it in the continuous sense. And then if you wanted to find the expected value of x squared, then you would just square this x right here. So that's how you would find the variance in the continuous sense. This
You
is,
might-
this is kind of an important one.
You might want to put the bounds between A to B.
Right, yeah, so from A to B of x, like the bounds that are given for x, you're gonna integrate it between that.
X squared? We're, because A of
So,
X squared.
If you wanted to find the expected value of x squared, because like you need to find that in order to find your variance, right? Because it's your expected value of x squared minus your x, yeah. So if you wanted to find that, then you would just square your x.
And if you were to find the expected value of X, Y, you would just do, it would be double integral?
It would, yeah, it would be a double integral, and you would use, so you do x times y times, and then you just use your joint probability. There you go. Yeah,
And just for the record, if it says it wants the expected value of X divided by a third, pretty easy. Set it up like that.
so, and then you can pull out that one. Okay, cool. Number two, if x is a random variable with CDF such as that, is it,
Can you move it down a little bit? It's kind of in between the.
oh yeah, sorry about that. Then it's a or uniformly distributed. What are the properties of a uniform distribution? You guys remember?
It's
Just a straight
flat
line.
on a curve. Or it's flat on a graph, yeah.
Exactly, yeah. So it's gonna look something like this. Oh, that's awful. So it's gonna be from point A to point B. And it's just gonna be like that. And do you guys remember the height of that? Did- who-
Whatever integrates to make it one.
Exactly, whatever integrates to make it one. So if we're trying to measure B minus A, so this is the length times height. It's gonna be the integration here because it's just a rectangle. So finding the area of a rectangle is just length times height. And so if B times A is our length, then that's it. Minus A, that's our length.
Let's divide by 2.
Times x equals 1, so then x equals over A. So this height right here, I guess, sorry, probably should have done y because that's easier to think about. So this height is always going to be 1 over b minus A. So that's the properties of a uniform distribution. So do we meet those properties here?
The X is a random variable.
It is.
And so. Does this imply that, this implies that we have enough samples, maybe, enough n.
So random variable just means that you can pick at random and it's going to be anywhere on that distribution. So it like you pick at a random x and it's either going to be, there's a 0 probability that x is less than 1 and wait. That's not the right way of saying it. Oh, there's our CDF. Okay, yeah, so
And notice the way that it's written, where you just plug in a value and it'll just tell you what the area is.
So this is roughly our CDF. So this is 1, 0. So as like So this line represents the area of any point between these two. That's kind of what a CDF is. And so like, as we go from 0 to 1, so like any point between, so like. I'm not making much sense today. So. See if I can put this into words.
I draw it out.
I'm gonna, give me a second, let me think about this. Yeah, so. We know that the CDF is from 0 to 10 on the axis. There we are. That's what the problem was. So from 0 to 10 on this axis, like at any point, the height is going to be like the probability of that. Or not the probability,
Area.
the area, yeah, the area. So for example, let's say like,
This is the CDF and then the uniform distribution is the PDF.
yes, yes, exactly. So it tells us right here that this is a CDF, and usually if there's an uppercase F, then that's our CDF. Lowercase f is our PDF.
And uniform distributions and normal distributions are both meant to be PDFs.
Yes, those are both PDFs, exactly. Yep.
We're trying to, so we're kind of like saying here, we're taking the integral of whatever we have going on here.
So kind of. It's like we have the integral of what we want to find.
So this is the integral.
This is the integral because it's the CDF. So to find the PDF, we would take the derivative.
Okay.
So our PDF is just a line of that's 1/10. That's our PDF. Which if it like if the height is 1/10 and then we need to know if the length times 1/10 is equal to 1. I'm sorry, I'm losing some of you.
No, you're doing good. You're doing great.
So there's no central limit theorem, it's all just about just if we were to graph it, it just looks distributed normally. And
Yes, exactly.
Thumbs up.
That's what this question is about. Like, is this like the CDF of a normal or uniform distribution?
Because when I saw this, I had the test in front of me. When I saw this, I was like, oh, random variable, central limit theorem. And then I just moved on. And so, yeah. But not always, okay.
But yeah, no, so random variable will just show up kind of all over this. Because a random variable just means like you're choosing random.
Okay,
There's another factor you're gonna wanna go over. So it's still gonna be 1 even if x equals 11. Right? So even if we get 12, it's still gonna equal 1, which
So past this 10, your CDF is just going to be equal to 1.
make it drop down to like the number line area. Like how the area goes to like 0. You know what I mean? Like it becomes
Sorry, we have our PDF here.
on the CDS. Like if it goes past 10, then it just goes to the number line to the bottom. Does that make sense?
So our CDF, this value, the value of the line is the area up to that point. So once you're up here, or sorry, not the area, but like, yeah, no, it's the area. Because once you're past there on the uniform distribution, then it's 0. So the area doesn't grow anymore.
Exactly.
So it's going to be all the way up.
And when you're. What I mean to say, Spencer, is that when you get past 10, it goes to the bottom because there's no more area to grab underneath the curve.
No, but the area overall is still 1.
Right, meaning it's 0, even though it might go on the scale on the x-axis, past 10, it's going to be hugging it, shall we say, asymptotic to it, like it's not gonna touch it.
I don't think we're thinking of the same thing here.
It's okay, don't worry about it.
What's up, Spencer? Sorry.
So if you were to very succinctly write in number 2, what would you?
I would say the PDF, well, yeah, I guess I'll write it right in the space. So the PDF is f of x equals 1/10. And then, so then I check to see, so we know that like if y equals 1/10, then that's a straight line at the value of 1/10 y. So we know that like this is 1/10 right here. So then I check to see if the bounds from A to B, so b minus a times 1/10 equals 1. Does that make sense? So if length times height equals 1, then our rectangle, then the area under the rectangle is 1. And then we, then it's a uniform distribution. If it does not, if the area of that rectangle is not 1, then it is not a uniform distribution. And that's kind of the property we're looking for here. And so we'd say, okay, the bounds are 0 to 10, so a equals 0, b equals 10, so 0, 10, 10 minus 0 is 10, and 10 times 1/10 is equal to 1. So it's a uniform distribution. Kind of a little bit clearer?
That's true.
It is true. Yeah. That one's true. Okay, number 3, to find the joint probability density function. Two continuous variables, you can multiply the marginal densities together. Is that true or false?
If and only if they're independent.
Exactly. So we talked about the definition of independence is the marginal distributions multiplied by each other. Like if they together make the original joint probability distribution function, then they're independent. And so then this is only true if the margin, if x and y are independent from each other.
So what would we write, true or false?
We would say,
True if they are independent, or false because we don't know that they are independent.
when approaching these problems, the idea is that it's going to make a statement. And you're going, like, it's under the assumption this is always true.
Oh,
So if it's not always true, you'd say false.
say false because we don't know if it's.
Although if you just explained your answer and you said true if they're independent, I would have given you the points because you know what's going on.
You get the concept.
Exactly.
Dr. Price says, so long as you can prove like mastery, like if you can make your assumptions and say, I'm gonna use 1.64 instead of 1.65. Even because it's in between or something like that, then he's like, yeah, cool.
Right.
You're able to list your assumptions.
I'm gonna real quick, because you guys have access to this answer key, I'm gonna real quick, let's, before we're done, there was a problem that I wanted to go over. But while I'm pulling it up, is there like any more questions that you guys have that you want to go over before finish?
What's the hardest question on the final?
Let me pause the recording so Dr. Price doesn't find out. I'm just kidding. It was a joke. Like dead silent here.
Have you guys ever been to, my friends said I should go, it's called salsa chocolate, that I should go.
Chocolate.
Yeah. They should, have you been there?
I dance. That's how
So,
my wife and I met.
Okay.
Well, it's not a salsa chocolate, but I'm BYU ballroom dance team. Are
okay,
you asking if you should go?
my friends are pushing me to go tonight. I don't know at all how to do salsa dancing. Would it be fun or do you recommend against it?
Get there early so you can be there for the lesson and you'll do just fine.
Okay,
But you're gonna be dancing mostly bachata, most likely.
what does that mean?
It's just a different style. It's a lot easier. It's a 4-step dance.
Okay,
You guys do that in swing dance? Or sorry,
I'm bad at swing dance. Is it,
Doesn't that happen on Thursdays though?
it's Thursdays and
Mondays?
Tuesdays, I thought.
oh, then I'll have it.
'Cause I think it's a different thing happening tonight.
And then,
Bachata?
Bachata.
Bachata is.
is it better to go with a group or is it better to just meet people there?
Go with your
Both.
Go with a group, okay.
Go with a group and meet people while you're there, for sure. But I feel like if you go with people, especially if you haven't gone, it's very fun.
Okay.
Yeah.
Cool.
Okay.
Okay, going back to.
No, thanks. It was awkward. I was hating it. So thank you guys.
Sure.
Okay.
Oh, I loved this one.
So this is a problem in one of the practice midterms for my class last semester. And so this is just a classic joint density problem. And let's, yeah, we can go through it. So if you guys remember, part Oh, we're looking at part two? Oh, no, question two, sorry, my bad. So if you guys remember, in order to find K, so it gives us like this scalar K. And it asks us, oh, can you guys see this? Is it too? I'll zoom in real quick. I want to make sure that it's able to be seen from the Zoom recording. Oh, I can't even check that because as soon as I check, then. Oh, yeah, you can't see this at all in the Zoom. Sorry, guys. The light is just glaring on it. Sorry, if you want this problem, I will post it and email me. You got it. So
Privileges.
we have this marginal PDF, or not marginal, this joint PDF. And we want to, it's got this scalar K. And to find that scalar, we already talked about this. We take the double integral and we set it equal to 1. Because the double integral is like,
We're trying to get the full probability of it.
exactly. So the full probability of it, you take the double integral and the full probability of anything is always just, you can have a probability higher than 1 unless you're Dr. Price writing a test. So
That was crazy.
I remember he swore, like, I promise, we're not gonna do anything greater than 1, and lo and behold.
I know,
I made this
that was
mistake in the
amazing.
spring. I'm not gonna make it again.
So the way you find it is you just do the double integral, dx dy, and you. Yeah, you set that equal to whatever, and we can go through this whole process if you guys want to.
Set equal to 1.
Yes, you set it equal to 1. Once you find kind of the final thing here, I'm just gonna check it real quick and not go through it all unless you guys want to.
No, just set it up for us.
Okay.
What's your favorite thing to do? Do you like to pull the two out and separate into two separate integrals, or do you like to keep them together? Like,
I'll just do one. I'll just do that.
you'll just do it.
Yeah,
You won't even split it apart.
Yeah, I just raw dog it.
Okay.
That was wild.
Well said.
Yeah, so it's going to end up equaling. Let's see. Oh, yeah. So you're gonna end up getting. I immediately forgot after walking away. So 2 minus k over 4 equals. So it's like, you're gonna end up equaling. 2. And it's don't make it
Minus k divided by what?
4, yeah. So then you're gonna end up like, 1 equals k over 4. And then k. And that's just, yeah, we're good there, sweet. So then part 2 or part B, find the marginal density of X. So do you guys remember that one? That's
Integral of Y.
exactly, thank you. So you take the integral of just
2 minus 4 xy.
4xy, y. And that is going to end up being,
Is it from 0 to 1, or do you not need the?
yeah, so you're gonna take it from 0 to 1 because 0 to 1 is still your
Okay.
bounds. Like for X and Y. It's really convenient when they do that and give you the same bounds for both variables. And so then this is going to end up equaling, I literally look at it and then I walk away from the I completely forget. It's 2 minus 2x. And that's your
X.
fx of x.
And is y just the same thing but with a y in it?
Yes, yep. And then by symmetry, because it's the same like on both sides for this problem, you'll literally get 2 minus 2y is your marginal distribution form.
That kind when they do that.
Yeah, it was super kind of me when I wrote this, because I wrote it absolutely. Yeah, what's up?
And so if we wanted to find the expected value of X, we just do X times that thing.
Yeah, you're getting ahead of me here.
Sorry.
Find the mean of x. Good. You wanna come up and try it?
Sure, yes.
Yeah.
Why not? I mean.
Real quick,
No.
you're gonna take the integral with respect to x. Oh, sorry.
You sure? No.
So to find the expected value, you use your marginal distribution. So it's gonna be two minus two x.
Oh.
It's the equation is.
Okay, that's where I got, okay, that's where I got lost. So it's not this, it's this.
Yeah.
Minus two x. The x.
Yep.
And just distribute the x, so it's. X squared. And then equal to two. Two squared. Plus 2, 3 x cubed. So that would just be 1 minus 2/3, which equal 1/3. No?
Oh, not quite. No, sorry, you are right. I was looking at the wrong answer. That's my bad.
So 1 minus 2/3, which is equal to 1.
Exactly right. Nice job. So out of curiosity, could you find the variance?
Variance?
Yeah.
Well, then you have to do that. Here, you want variance.
If you want to, but.
But then you're just
Yeah,
like.
exactly.
You
You'd
find
find
like
x
that,
squared.
you distribute it and then integrate it.
Mhm.
But
And then you'd subtract
And
one
then-
squared.
yeah. This, wait,
So, yeah, the x
and then
squared,
you do this one squared, so it'd
Yeah.
be this minus 1. Oh.
squared.
Yep. Exactly right. Did everyone follow that? Like, any questions on that part? Yeah. Okay. I'm running out of time. So we can check for independence. And
Spoiler alert, I don't think they're independent.
you don't think they're independent? Why not, Taylor?
Because they're never independent.
Oh, okay.
Can we do independent?
Yeah, let's do it. R and Y are independent. So, an earlier part of the question. Scroll up top a little bit so that it's not quite. There we go. So. An earlier part of the question was like, it says by symmetry, they're gonna be the same. So your marginal distribution of Y. Is going to be equal to 2 minus.
You know how I know they're not independent?
Enlighten.
Because they're gonna ask us to find the correlation of it, like, the next step.
It's true, yeah.
So they're not gonna make us do that. That's why, they're never independent because of that.
That's true. So to find independence, what's the easiest way to find independence, Taylor?
Take the marginal distribution times the other marginal distribution of x, one of y, and set it equal to the joint distribution. You know, once you write it out, we can go over that.
But what's the easiest way?
I mean, plug in 0 for each of the variables. And see if they
Exactly.
equal that.
So our original function is
F of
2
x
minus
0.
4xy, right? So if we plug in 0 there, 0 times 4 is 0, so 2 minus 0 is 2. So then if we plug in 0 here, we get 2 minus 2 times 0 is 2 minus 0, so that's 2 times 2 minus 2 times 0, so 2 times 2 is 4, which is not equal to 2, so they are not independent.
Big sad.
We good? Makes sense?
Those the two marginals multiplied together is equal to the joint distribution.
Yeah,
Marginal times marginal is joint.
exactly. And if that is true, then they're independent. This is your marker for independence.
And what happens if they're independent?
If they're independent, then you go home and everyone's happy. Turn in the test and the testing center gives you a big gold sticker. No, I have no idea. If they're independent, then
The correlation is 0.
it's 1.
1.
or sorry,
Yeah.
Zero.
0, you're right, that's my bad.
And if correlation is 0, that doesn't mean there's no relationship, that just means there's a non-linear.
Exactly.
Possibly.
Yep. So that's kind of brief overview of part 2 of the class. Are there any more specific questions that you guys have?
Can we go over the last one on the test for the number 2 test? Number 12.
Yeah.
I can, or if, or, I don't know.
12 down here.
Maybe other people will find it interesting, but I got it wrong on the test, so that's. That's fine.
It was a beast.
Okay.
My sample, oh yeah, 10 was a monster.
Was that the one that was just like, here's a whole bunch of just like random things to do?
It felt like homework. It was like, get it, you got bored. Like, you can stop writing the test now. It's okay.
Yeah, so let's go over this one.
How is that test looking, that final looking? Is that looking like 22 pages still, or?
So he said 22 pages. I looked over it. About 5 of those pages were the graphs at the end, like the distribution. So it's only 17 pages. But no, we talked about it and I don't know what he's
Are we
doing.
are we gonna have access to like the actual tables and things like that, or is it gonna be the ones from the past test? Are we gonna get like the ones with the formulas on them, like they have on the website?
Probably not. Probably not.
I can check actually real quick, but
How long?
I mean, I'll ask them on Tuesday, but
How long is the time on that?
there's no time.
No.
Yeah, so it's in the testing center.
isn't it the testing center?
It is.
Even though learning's free, said otherwise for a while.
Yeah, it did for a little while.
Still,
Oh, wait, so
But it is in the testing center. It's open through the remainder of finals. Okay, go over 12 real quick. So why is a sample mean a good estimator for population mean? Like, what does that even mean? What makes a good estimator?
Unbiased. And consistent.
Exactly, that is exactly right. So unbiased means that the expected value of your estimator is your parameter. Which you can show mathematically through proofs, which I would not spend my time studying proofs for this exam.
okay.
That's for 388, guys.
That one class that we did, that the entire class was just to prove like that one, like why sample variance is 1 over n minus 1. That was crazy.
It's cool stuff. It's pretty interesting if you're into that stuff, but I would not spend my time studying proofs for this test. Then consistent, right? We already talked about as your sample size gets bigger, variance goes down, and so does your bias. I mean, bias is already at 0 for sample mean, right? Because there's no bias in that. Oh, I erased it. I keep pointing to stuff I erased. But
Remember?
yeah, if you guys remember, visualize it, think about it. It was there at one point. But yeah,
Are there prerequisites being unbiased and consistent, or like, do we need IID to have those?
so IID, it helps. Okay, so IID,
Makes it
if
more,
it's not IID, then it is going to be biased.
okay,
And so the reason we need IID is to kind of remove that sample bias.
and so to answer this, we could just say it's unbiased, consistent, to get these, we need IID.
Pretty much, yeah.
Thing.
The answer key literally says like, it's unbiased, it's consistent. That's what the answer key says, so
Good to know.
awesome. Any other questions, last minute?